Alright, so it's time to make some more discussion about electron dot structures. We need to do some that are a little more complicated and in more detail, and find a pattern to how we can predict these for all kinds of compounds. The idea is that we want to hope for an octet in a general sense. However, it does not always hold. Boron was one example, but other elements that do not adhere to the octet rule always are going to be those who are from elements group 3A through 8A, in other words, nonmetals that are in the third row and lower. And why is that? Well, it boils down to electrons in the fact in those third period elements and below are going to have D subshell electrons available. They have they are able to accommodate more atoms in their structures than just an octet sometimes. Okay, so a general method that we would like to work with that helps predict the electron dot structure of just about any compound, there's sometimes some odd ones, but mostly this works, is going to feel a little different from the one we've looked at so far, because we're going to take a skeletal structure for a compound and then fill it in using this method, and it'll end up getting our bonds and the lone pairs and octets for each atom as often as possible and correctly done. Okay, so step one, you're always going to look for the total number of valence electrons. Well, valence electrons correlates to the group numbers, so most of the time that's not too hard to figure out, and you'll need to add that up for all the atoms in a molecule. But then you have to add in a few more electrons here and there, because you're going to have extra electrons when it's a negative charge, or you'll have to subtract some from your total if you have a positive charge on a cation. So we'll come back to some examples for cations and anions, but let's start with something more uncomplicated like sulfur tetrafluoride. So how many total valence electrons? Sulfur is group 6, so there's 6 electrons there. And then fluorine, well, let's see, group 7 still. So 4 times 7 is still 28. And so 6 plus 28, if you can do your quick math here, I hope that looks like 34 electrons. All right, so what we'll end up doing is we'll draw lines to represent bonds between the atoms, and hydrogen and halogens are simply going to be expected to form one bond, and elements in the second row can typically form a certain number of bonds based on their column, but there will be sometimes we see more than an octet, and so the initial thought is to put sulfur surrounded by 4 fluorines, and one line represents one bond to each of the fluorines from sulfur. Remembering how to put these together does take some thinking on occasion. You're not always sure which way to arrange the atoms sometimes, and the general rule is that the least electronegative atom in a compound is typically going to be the central atom. In other words, it's the one that's closer to the middle of the periodic table. They make more bonds in a general sense. And so going back to table 4.4 helps us recall the numbers of bonds typically formed by each atom. And table 4.4, oops, I don't have it here, I thought I did, will show you which elements have which numbers of bonds. Okay, so step 3. We had made bonds to 4 fluorine atoms from sulfur, and so that would be 8 electrons so far. And we're going to take that away from our total of 34 that we expected in this diagram. And so we figure out how many remain. So 8 from 34 means you've got 26 to go. And so 26 will be represented in the structure when it's done correctly. So what we'll do next is to complete octets. We'll complete octets for what they call either terminal or peripheral atoms. In other words, the ones not in the middle. And so in this case, there are 4 fluorine atoms, and each of them needs an octet. So 4 times 6 electrons, that would be a total of 24, because you've got 3 lone pairs around each fluorine plus a bonding pair satisfies an octet for each fluorine, for a total of 24. So now between the bonds and the lone pairs, 32 electrons are represented in this structure. Well, apparently we still have unassigned electrons, and in other words, we haven't got to that 34. So there's some remaining. We're going to have to put them on the central atom. So for this structure to be complete, sulfur is going to end up with more than an octet, because otherwise you've not accounted for all the normally occurring electrons for sulfur. So where does that result? It's going to give us a structure, that has sulfur in the middle and 4 bonds to fluorine plus a lone pair. This structure is not very elegant, but it makes the point. So each of the fluorine atoms has an octet, and the sulfur atom has 2 extra electrons that go beyond the octet. So those 2 are kind of shown in a funny spot here, but there is the octet for 2 of the fluorines. Here's the 3rd fluorine and 1 more fluorine, but the sulfur has 4 bonding pairs plus 1 other one, so it's more than an octet. There's 10 electrons around the sulfur. How does that work out? Well, you end up with something that could be more elegantly drawn with bonds for lines for bonds, and some folks like that better. It doesn't allow you to count your dots to add up the total number of valence electrons, but as long as you recognize that a line represents a pair of a pair of electrons, that works out just fine. So if you've counted them up carefully, you should have 24 around 4 fluorine atoms. In other words, 8 times, 32. 8 around 4 fluorine atoms plus 2 more extras on the sulfur atom for a total of 34 electrons in the structure. There's many more examples that we can do. I'll do a couple more for the moment and see if this helps you. We'll follow out the whole pattern. We did not use the extra rule that was shown as step 5 about unassigned electrons remaining after filling up the central atom. In that case, we'll end up making multiple bonds. Well, that didn't happen to be necessary in this example. So let's look for some more options that give us more examples of how these are used. Well, let's continue on down and look for a structure for something not too complex. Nitrogen trifluoride, following the steps have been described so far. So, start with what? Step 1 is to put the least electronegative atom in the center. In this case, would be nitrogen. And it's less electronegative than fluorine. Anything is less electronegative than fluorine. And so you make a skeletal arrangement of atoms, and we kind of use a rectangular grid because it's sort of convenient, but that doesn't exactly represent the actual geometry, which is shown there on the right, which is where we end up. Step 2, count the valence electrons. So nitrogen has 5, fluorine has 7, based on their positions in groups 5 and 7 of the periodic table. And we've looked at these configurations that should look familiar to you. So 5 plus 3 fluorines is a total of 21 plus 5, 26 electrons total. Step 3 has multiple parts here, so we're going to make single bonds between the nitrogen and fluorine atoms. And so single bonds are always 2 electrons, and so 3 single bonds gives us 6 electrons. And after we've done that, let's see, we'll have single bonds, there you go. Then we want to complete the octets on both the nitrogen and fluorine atoms. And so the fluorine atoms will require quite a few more electrons. So each fluorine atom, wrong way, there we go. But each fluorine atom is going to get 6 more electrons, and the nitrogen gets 2. And so you've got 3 times 6 is 18, plus 2 more is 20 electrons by lone pairs, by putting them around the fluorines and and 2 more on the nitrogen. Then we need to check the electrons in the structure and make sure that the ones we've represented equals the total number. Well, the total number is 26. So this structure feels like we've done the right thing, but it's always worthy to follow out the rest of the steps to make sure it hasn't lost anything. So 3 single bonds, 3 times 2 is 6, 10 lone pairs, count them, 2, 4, 6, 8, wait a minute, 1, 2, 3, 4, 5, 6, 7, 8, 9 lone pairs on the fluorines, plus 1 more on the nitrogen makes 10 lone pairs, adds up to 26 valence electrons. All atoms should have octets when we've done this properly, assuming there's no hydrogens here and no expanded octets. In this case, we don't have any exception there. the octet should bear out so that we have what we expected on each atom. All right, so another one, let's do the carbonate ion. The carbonate ion requires us to use another step because we now have to add electrons for the charge in the total valence electrons. So step number one is to figure out what atom goes in the center, and this time it's going to be the carbon, because carbon is very commonly in the middle of structures, and oxygen is certainly more electronegative, so carbon goes in the center, and we'll make a skeletal arrangement as shown at the bottom there. Then you count up the valence electrons that the structure should represent. Carbon is going to have 4, oxygen is going to have 6, but there's 3 of them. And then you have to add 2 more to the total for the -2 charge that is known for carbonate ion. So 4 for the carbon, 3 times 6 is 18. So 4 plus 18 is 22, plus 2 more is 24 valence electrons total when this whole thing is put together correctly. Step 3, draw the single bonds between the carbon and oxygen atoms. So 3 single bonds is going to be 6 electrons. And then you're going to complete the octet on the oxygen atoms. And so what do we have to have? Well, after the single bonds, then each oxygen needs 6 more electrons. So that would be a total of 18 around the 3 oxygen atoms. There you go, 18 electrons. Now, we have 6 plus 18. That means we've added up to the total number of electrons that this structure should need. And so what are we going to do now? Let's see. Okay, so we've got 3 single bonds, 6, and a bunch of lone pairs, and we added them up. It was 24. Well, what's lacking? Are all of the atoms containing octets, represented with octets? Well, not carbon. So this is when the last rule comes in. You need to form a double bond. And when we do this, what we end up doing is making a multiple bond between carbon and oxygen on one of the oxygens. It doesn't matter which one because they're all the same. And then you remove one lone pair from that oxygen so that it only has an octet and nothing extra. We haven't added any electrons, but we've just filled up the octet by rearranging electrons between carbon and oxygen on that particular one on the right. So 2 single bonds makes a total of 4, 1 double bond is 4, and a bunch of lone pairs. Altogether, we still get 24 electrons, and the structure is represented with this ball and stick diagram on the right. We'll talk more about those before this chapter is done. All right, let's try another one that has a charge and ion, and this time we'll do the nitrite ion. The nitrite ion, NO2 minus, so which one goes in the middle? Which one is less electronegative? I would certainly suppose that would be nitrogen, less electronegative than oxygen, so we're going to put the nitrogen in the center, and then we're going to count up the total valence electrons. So what will we have? So nitrogen has 5, and we have 2 oxygens, so each oxygen has 6, 2 extra, 2 times 6 is 12 plus 5, and that's 17, but we need 1 more extra for the charge, and so that is a total of 18 electrons. All right, so nitrogen's going in the center. You're going to need to put 2 oxygens with it, and we'll start out with that skeletal arrangement, and then we'll put single bonds between nitrogen and oxygen, 1 each there for the time being, and that's 2 electrons in each bond, so we have 4 electrons. Then we have to complete the octets on the oxygen atoms, and that requires a bunch more dots. Having added 6 electrons in lone pairs around each oxygen is 12 more electrons. What do we do next? So is the number of electrons in the structure equal to the total number of valence electrons? Well, we have 4 plus the 12 is 16. Nope, not enough yet. We need some more electrons. We need 2 more because we haven't hit up to 18 yet, so 2 more electrons are needed. So we have 2 single bonds, so 2 times 2 is 4 electrons. And how many lone pairs? It looks like 1, 2, 3, 4, 5, 6 lone pairs. So 6 times 2 is 12, and so that's a total of 16 valence electrons represented in the structure. So, do all the atoms have octets? Ooh, not yet. So what do we have to do? We need to fill in some octet around the nitrogen atom with the last 2 electrons. And so put the lone pair on the nitrogen. Recheck the total number of valence electrons. And now we're up to 18, which is the right answer because we just added 2 more. And we wanted a total of 18. However, does the structure represent octets on all the atoms? Not yet. The nitrogen only has 6. And so how we accommodate a structure that represents octets on everything means that we have to remove some electrons from one of the oxygens, doesn't matter which one you choose, and reassign it as a double bond to make that into an octet for the nitrogen. So 1, 2, 3 single bonds plus a lone pair is normal for nitrogen, giving it an octet. 1 single bond and 3 lone pairs being an octet for oxygen on the left. A double bond plus 2 lone pairs, noticing the one on the top here is no longer counting as electrons, we reassigned it. And the only thing that's lacking here is a representation of the fact that the entire structure has a negative charge, because this is what we call a molecular ion. Alright, one more compound that's not particularly complicated, but let's see if we can do it. This would be arsenic tribromide. So what atom is more electronegative than the other and or near the center of the periodic table? That's the one that's going to go in the middle. Let's make it arsenic. And it's less electronegative than the halogen, so we'll put the arsenic in the center. What's our next step? Then we'll make a skeletal structure. Arsenic surrounded by 3 bromine atoms, and then we'll have to start counting up the valence electrons. And so we'll have to think about where is arsenic? What group is arsenic in? Well, it's below nitrogen, so that would be in group 5. And so the total number of valence electrons there will be 5 for the arsenic, and then 3 times the number for bromine, 3 times whatever it is, well, that would be 7. And so we have a total of 5 plus 21 is 26 electrons. So we're going to put single bonds in between the arsenic and bromine atoms. So count up that each of those bonds gives you 2 electrons, 2, 4, 6 electrons total. And then we're going to have to complete octets on all the bromine atoms to fill up their octets. So that's 18 more electrons in those lone pairs around each of the bromine. So what's the next step? Let's think. Where do we have to be here? Well, we've shown 6 plus 18 or 24 electrons. So the number of electrons in the structure is not the same as the total number of valence electrons yet. So what do we do with the extra pair of electrons? We haven't got to 26, we've only got 24. And so in other words, double check yourself, make sure you're thinking right. We've got 3 single bonds, so 3 times 2 is 6 electrons, plus 3 lone pairs 3 places, so that's 9 lone pairs. So 9 times 2, and that gives us so far 24 valence electrons. Make sure you're not missing anything, because that's really half the battle here, is to make sure you've included the correct number of valence electrons. So if we haven't got enough yet, do all the atoms have octets? No. Arsenic needs another pair of electrons, so we'll add a lone pair to the arsenic, because that's where we'll go before we do anything else. And once we've done that, recheck our total number of valence electrons. Well, now we have 24 plus 2 more. That would be 26. And that was the goal for this diagram, for representing this structure for arsenic tribromide. So that should be what that structure requires. All right, let's include one more example of how we do an electron dot structure. Let's do carbon dioxide. Carbon dioxide, we'll have to start with coming up with the total number of valence electrons. Whoops, back it up. The total number of valence electrons then is going to be what? Well, carbon is going to be 4, and 2 oxygens are each 6, so that's 12, and that means a total of 16 electrons. Pardon my crude drawing here. This is being done with a mouse, not the easiest thing. And so we'll have to figure out how we arrange them. So carbon goes in the middle and one oxygen on each side. We'll start by adding one pair of electrons on each side for bonds. And so we're going to make bonds. And how many electrons did that use? Well, that would be a total of 4. So we'll subtract 4 from our total. That we will figure out what belongs in the structure after that. We need 12 more to go. And so we'll have to fill up octets around the oxygen atoms. And so 2, 4, 6 electrons on each oxygen adds up to a total of 12 electrons, right? Well, that's how many we had left to do. So oxygen's octets account for the remainder of our total number of valence electrons. However, does each atom have an octet? Well, no, because carbon is only shown with single bonds, and that's only 4, not an octet. So in order for us to accommodate an octet for carbon, we have to reassign some peripheral electrons into a lone pair, or sorry, into an extra bond, a multiple bond for carbon. And if I picked a pair off the oxygen on the left, well, that gives us an octet for the oxygen on the left, but not yet for carbon. So we'll do it twice. And so 2 electrons are reassigned as a bond again from the oxygen to the carbon. And that gives an octet for oxygen with 2 lone pairs and 2 bonds. But now carbon also has an octet with 2 double bonds. And that works out to be enough electrons to add up to 16 electrons, remembering that you have 4 electrons in each double bond, so that's times 2, and that would be 8. And add to that the 4 electrons in lone pairs on each oxygen, so 2 times 4 again, and that adds up to a total of 16. So the structure for carbon dioxide includes 2 double bonds. And you can look at the diagram at the bottom of the structure page and see that you can either use dots for your bonds or you can use lines for the bonds. Either one, as long as you recognize that a line represents a pair of electrons. All right, that's a lot of examples. I hope you find that useful as you work through your assignments with Lewis structures.